Find the determinant of the following matrix. Specify whether the matrix has an inverse without computing it. So in addition to the 3 row reduction properties that we've just reviewed, we want to keep the following theorem in mind. So let's recall that if A is an n by n triangular matrix, then the determinant of A is the product of entries along the main diagonal. So this lets us know that in finding the determinant of A, we need to row reduce the augmented matrix to just echelon form. So we want to row reduce matrix A augmented with our 0 vector to echelon form, a triangular form. And again, you want to keep in mind as we go through this row reduction process that each of the row operations affects the determinant. So make a love note here to ourselves to be mindful of how each row operation affects the determinant. So we're ready to begin. So we are augmenting matrix A. So I have 1, 3, 2, 5, minus 3, 13, negative 3, 3, minus 7. And then we are augmenting this with the 0 vector. And so using our first pivot position here, we want to use this to eliminate the entries below. So we'll do minus 3 times the first row plus the second row to attain the new second row. And since this is combining, there is no effect. We'll also do minus 2 times the first row plus the third row to attain the new third row. So again, if both of these operations are combining, so there is no effect on the determinant. So this will be equivalent to, row 1 is the same, 1, 5, negative 3, and we have minus 3 plus 3 is 0, minus 15 minus 3 is negative 18, positive 9 plus 3 is 12, and then we have negative 2 plus 2 is 0, negative 10 plus 13 is 3, and then positive 6 minus 7 is minus 1. So our first column is good, and moving to the second pivot position, we notice that row 2 has a scalar multiple. So I want to scale the second row here by a factor of 1/6. Now we want to be mindful here, since we're scaling, this row operation affects the determinant. So since we are reducing the second row by a factor of 1/6, we're going to need to multiply the determinant by its inverse. We need to multiply it by 6. So in our next step here, we want to keep 6 on the outside of our augmented matrix to remind us to multiply the determinant by 6. So we're left with the matrix 6, or 6 multiplied by the matrix 1, 5, negative 3, 0, minus 3, 2, and then 0, 3, negative 1. So again, using our second pivot here, we want to use this to eliminate the entry below it. Fortunately, we can do so by simply adding the second row to the third row to attain the new third row. And since we're just combining, there is no effect on the determinant. So this is equivalent to 6 multiplied by the matrix 1, 5, negative 3, 0, minus 3, 2, and then 0. So we have 3 minus 3 plus 3 is 0. 2 minus 1 is 1. And we're excited because we have attained echelon form, which is a triangular matrix. So we can conclude now, using our theorem and properties of the determinant, that therefore the determinant of matrix A is equal to 6 multiplied by the product of the entries along the main diagonal, which is 1, negative 3, 1, for a beautiful final answer of negative 18. And we can add one more little love note here, that since the determinant of matrix A, which is negative 18, does not equal 0, we know that A is invertible, or singular. So now that we've used our properties and our triangular matrix theorem here to find the determinant, we can go ahead and confirm that this is in fact the answer using the definition of the determinant. So let's take a peek. So to check the determinant we computed using the properties and the triangular matrix theorem, we can compute the determinant using the recursive definition or cofactor expansion. So here, since we have just a 3 by 3 matrix, we can use cofactor expansion across row 1, which is equivalent to the recursive definition. And so for the first entry in row 1, we eliminate the adjacent row and column. For the second entry in row 1, we eliminate the adjacent row and column. And the third entry in row 1, we again eliminate the adjacent row and column. And what this does is produce the submatrices for each entry. So this would be technically 1 multiplied by the determinant of our 2 by 2 matrix here, 3, 3, 13 minus 7, and this is minus 5 multiplied by that 2 by 2 submatrix, 3, 3, 2, negative 7, plus or minus 3 multiplied by the 2 by 2 submatrix, 3, negative 3, 2, 13. So now we are ready to compute the determinant of each 2 by 2 submatrix. So case 1 here we have negative 3 times negative 7 for a positive 21 minus 13 times 3, which is 39, minus 5 multiplied by negative 21 minus 6, minus 3 multiplied by positive 39 minus a minus 6 or plus 6. And so this is leaving us with 21 minus 39, which is negative 18, minus 5 multiplied by a minus 27, minus 3 multiplied by 45. So we have negative 18 plus 135 minus 135. And this leaves us with our beautiful final answer of negative 18. So we have confirmed that the determinant of matrix A is equal to negative 18. And we can see here too, since each one of these 2 by 2 submatrices has a non-zero determinant, right, minus 18, minus 27, 45, that this matrix A is invertible. Which we confirm from the non-negative determinant.